Hey, what's up, guys? This is Chung here again. So this time, LeetCode number 2019. So the score of students solving math expression, right? So this time we have a string s, right? So which contains only the digits from 0 to 9, and then only two symbols, addition and multiplication, right? And then obviously we have like a correct order of operations, right? Which is to compute the multiplication reading from left to right, and then compute addition reading from left to right, right? But some students, and then we're given like this expression to n students to ask them to evaluate this answer, this expression. And some students might get the wrong answer by using the wrong order of the operation, right? So, and that's why, so if a student gets the correct answer, he gets 5 points. Otherwise, if a student gets an answer by applying the wrong order of operations, he gets 2 points. Otherwise, gets 0 points. Okay. So for example, we have this 7 plus 3 plus 1, we have this expression 7 plus 3 times 1 times 2, right? So apparently this one, the correct answer is what? It's 13, right? But some students, they could have like applied the wrong answer, which means they could have applied evaluate this part first and then this part, which means in this case we have 10 times 2 equals 20, right? That's why for 20 we get 2 points, right? And for 13 we have 5 points. For 41 it's 0 because no matter how we change the order of operations, we'll never get 42. That's why the total points for this one is 7, right? And yeah, so we have a bunch of other examples here, and then the constraints like this. So the string is 31, right? And then the times of this, the total number of operators 15, right? Apparently this is right because since the string is like 31, right? And then the answer is like, and then the operator is one number and one operator. That's why the operator is within 15. Okay, and the test data are generated within this one 1000. Okay, basically it means that the answer will be smaller than 1000, right? And we'll need this one to do some optimizations later on. And then we have this kind of total n students, right? So for this one, actually, what we have, let's give an example. We have 1 plus 2 times 3, right? And then plus 4 times 5, okay, plus 6 times 7, right? So here, let's say, so, since, like I said, since we can use any order of operations as we want. So what does it mean? It means that, let's say, we can add a parenthesis like this, right? So this is one way of doing it, right? Or, oops, okay, sorry, my mistake. Or we can add a parenthesis somewhere here, right? Or somewhere here, somewhere like here, right? So basically, as you guys can see, we can add like any parameters, any parentheses and then to split this expression into two parts. So which means we need to, given like this possible like operations, we have so the last operator is a multiplication, right? And then we have the left and right, right? So let's say we have on the left side, if we have 10 possible values, and on the right side, let's say we have two possible values. I mean, ignore this the examples here. And then how many total values we have here? So we have 10 times 20, right, equals to 20. Sorry, 10 times 2 equals 20, which means we'll have like 20 possible values given like this kind of combination, right? But that's not all, right? Like I said, we could this one could be the last operator, or this one could be another one, or this one could be a last operator, or this one could be a last operator, right? And we have to consider all the possible values, right? And since we have and as you guys can see, right? I mean, once we have fixed the last operator, now the expressions are divided into two sub expression, right? One on the left side, and the other one is on the right side, right? So and then naturally we should use now this will lead us to a DP solution, right? Um, yeah, so this one will lead us to a DP solution because um, for the same sub expressions, we don't want to calculate them multiple times, right? Because we could have, since we could divide this strings into in many ways, those one sub expressions can be used more than once, right? That's why naturally we should define like dp uh, dpi and j, right? So this one equals to the total all the possible values, right? Values for expression, right? I to j, right? And then what's going to be the time? Sorry, the state transition, right? So like I said, we have to try all the possible sign as a last operator between I and j, right? Which means, let's say we have a sign, we have this one, this is sign, right? And then we have what? We have dp of I to sign -1, right? Times dp of sign +1 to j, right? And then we have to do this summarize for all the signs, right? From I to j, right? So that's basically the state transition function. Okay. Yeah, I think that's it, right? So let's try to start coding then. Yeah. Let me remove this. Okay. Cool. We need the dp function here. Okay. And then we have a defined dp of I and j. Okay. So how about the base case? So the base case is apparently when I is equal to j, so we only have one numbers left, right? That's why we just need to simply return this one number as an integer. Okay. So since when we do the evaluations, we need to do a times b or a plus b. That's why we need to convert this string to integer. Okay, and then here we're returning a stat, right? Because here we're gonna define the candidates as a stat, because we we could have multiple like values. We could have a multiple branch which will lead to the same value. That's why we use a set. And then here we just try all the possible sign in range from I plus 1 to j, and the step is 2, right? Here we try all possible sign as the last operation, right? from I to j, right? Because we have 1 plus 2 plus 3, so we have I and j, right? So the first sign is I plus 1 is this one, right? And the step is 2. Okay. And after fixing the last operator, right, we have left and right. So the left will be for a in range from I to sine minus 1, right? And then for b in dp of sine plus 1 to j, okay, right? We have result equals to a times b, right? If this s sine equal to star, right? Else we use a plus b. Okay. So here, and we have a candidate, this result, right? So let's say if we don't use this constraints, this will TLE. Here we return the candidates in the end, right? Okay, let me finish that, then we'll try to improve that later on. So, and once we have DP, all we need to do is we just need to call it DP with the length from 0 to length s minus 1, right? So here we have all the possible values, and we also need that a true value, right? The true value we can just use evaluate function, the built-in function to evaluate this as. Then we have answer equal to 0. So for a in answers, right? So if the a is equal to the true value, okay, right, we got 5 points, right? Else if the a is part of the possible values, right, the the wrong answers, one of the wrong answers, we got 2 points, right? If the a is not even in this possible wrong answers, right, we'll simply ignore that. So we return the answer. Okay, so I think that's that. So if I run it, okay, so this one accepted, and if I submit it, this will TLE. So the reason being is like this. So we don't optimize anything here. So which means on the left side and the right side, right? So basically we'll have too many of the wrong possible answers being returned from both left and right. Because let's say if we have a 1,300 and we have a 400 here, so apparently we should drop this 1,300 on the left side, because this one has already exceeded our biggest possible answer, which is 1,000, right? That's why in order to pass all the test case, we should check this. So if the result is within 1,000, and then we add this one to the candidates. Okay, let's try again. Okay, right. So now it passed. Yeah. So, and for the time complexity, right? Let's see for the time complexity. So for top-down DP, right? So the time complexity equals to the number of the states times the time complexity for each of the DP function, right? Inside each of the DP function. So let's say we have this I and j is the so this is the 15 and 13, they're pretty much the same, right? So this one for I and j we have, let's say this one is in M, right? Yeah, let's say if this one is M, right? And here we have total answers. The total answer is 1,000, right? So here, this n is like the last one. We can ignore this one because this part, the DP part, will be much heavier than this for loop here. So we have this M, and then we have this total answers here, right? So let's say this one is let's not use n here. Let's say this one is k, possible answer, right? So we have this one. This one we have m square, right? And then inside here we have what? We have a sign, right? Sign is like another m, right? And then we have a nested for loop for the left side and right side. Okay, you know, theoretically, both the left side and right side can give us at most 1,000 answers, right? Because this both the left hand side could have all the possible answers with 1,000. That's why this one is kind of a k square. So basically, the total time compressed is going to be m cubed times k square, right? For this dp. Yeah, and as you guys can see, so the k square itself is 1 million already, right? And then times this 15 to the power of 3 or 15 cube. This one most likely will TLE. That's why if we don't have this kind of optimizations, the first run got TLE, right? And yeah, but I think the in the reality is that the sub problem, so the sub problem of left and right, we will not have this all the 1,000 answers if we have this kind of optimization, right? So it seems like in order to pass all the, the test case, we have to add this optimization to reduce both the left side and right side to like a manageable amount count, right? And yeah, I think that's it. I mean, this one, uh, it's like this one reminds me of another uh, problem called find all possible binary tree, right? So for that one, I think similar, right? Basically, we try to break the tree in all the different ways, and then we'll have left and right, right? And then we'll do the similar thing, right? We try try all the root, right? Basically here, this is more like a root, and then we divide this one into a left and right part, right? And then with all the possible left and right part, we'll do like the combination, right? And we'll try to combine each of them to get the possible answer for the current layer, right? Yeah, and then other than that, we just use like a set to track all the possible candidates, and so that we can use them later on. And yeah, the last thing is to just remember to cut some invalid branches in order for us to pass all the test case. Uh, yeah, I think that's it for this one. And thank you for watching this video, guys, and stay tuned. See you guys soon. Bye bye.